Hello everyone. So today I'm going to introduce some of the notation, some of which I've been sweeping under the rug in the context of topics we've already covered, and some that's going to be important for upcoming lectures. So I'm sure some of you have been clamoring for this, for this level of precision, and others of you are dreading it, but today is the day, and so let's get started. Okay, so what I'll talk about today is, well, first I'll start by talking about the Ket notation. So this is just completing this Ket notation that I already introduced. Then I'll talk about Hermitian operators and the Hermitian matrices and their eigenvectors, eigenvalues. And finally, I'll talk about tensor products of Hilbert spaces, tensor products of matrices, etc. Okay, so let's get started. Okay, so just to make sure we're all on the same page, so far we've been talking about quantum states, which, let's say we are working in a k-dimensional Hilbert space, k-dimensional complex vector space. So our quantum state is a k-dimensional vector with k complex entries. And in our Ket notation, we write it as alpha naught 0 plus alpha 1 1 plus so on, alpha k minus 1, k minus 1. So just to remind you, Ket notation was introduced by Paul Dirac, the great physicist. And the useful thing about the Ket notation for our purposes is that it at the same time represents the fact that the state is a vector and that it conveys information. So for example, if you had a qubit, we could write its state as alpha 0 0 plus alpha 1 1. But we could also write it as, maybe we don't want to write the states as 0 and 1. Maybe it's a spin state and we want to write it as alpha 0 up plus alpha 1 down. Or maybe we want to write it instead as alpha 0 blue plus alpha 1 red. Okay, so the great thing about the Ket notation is that it makes it very convenient to talk about a label for each vector in the basis. And at the same time, it allows you to express what the amplitudes are, or the entries of your vector. Okay, so now, corresponding to this vector, which we'll call Ket psi, there's a corresponding vector which we'll call Bra psi. And this is the conjugate transpose. It's a row vector, alpha naught star, alpha 1 star, alpha k minus 1 star. By star I mean just, of course, complex conjugate. And we'll denote this vector by this symbol. So where the pointy end is to the left. And so together with the Ket, this forms Dirac's Ket notation. Okay, so now suppose we have another vector or state phi, which is beta naught 0 plus beta 1 1 plus so on, beta k minus 1 k minus 1. Okay, so then what's the inner product of psi and phi? Okay, so if you want to write out the inner product of psi and phi, the way you would do it is you would take alpha naught star, alpha 1 star, alpha k minus 1 star times beta naught, beta 1, beta k minus 1, which is just summation over j of alpha j star beta sub j. Right? That's your inner product. Now, how would we write it in our Ket notation? So the way we write it in the Ket notation is this is bra psi, and then we write a ket phi, and we don't duplicate the vertical line in the middle, and so that's our notation for inner product. Okay, so now we can also, of course, once we have an inner product on our space, we can define the length of a vector. So the norm of psi, or its length, it's just the inner product of psi with itself, and then the square root of that. Okay, but what would that end up being? Well, that'll just end up being square root of the summation of alpha j star alpha j, which is of course the square root of the summation of alpha j magnitude squared, and that's our usual notion of length of the vector. Now, the other thing you can, the other thing to, if you wish to think about it intuitively, then the inner product gives you a natural notion of the angle between two vectors. So if this was phi and that's psi, then somehow we want to think of the inner product as telling us what this angle theta is between these two vectors, and so it tells us what cosine theta is. Well, but of course you have to remember that in general this inner product is going to be a complex number, and so if you want to make sense of what angle means, we could sort of say the angle between these two vectors could be defined like this. The theta could be defined like this, where cosine theta is just the inner product between psi and phi. It's absolute, its magnitude divided by the length of psi times the length of phi. Okay, that's just an intuitive notion of what the it's interpreting what the angle between two vectors is, and here we'd of course want theta to be between 0 and pi over 2. Okay, so for example, you see the reason we want to do this is because if we were working with just real vectors, then of course we might have this situation, or it could be that we had minus psi, and if we had minus psi, then the inner product would be negative of what it was here, and of course the angle becomes pi by 2 plus theta. And so we could do something similar in general. Of course, if we are working in the complex plane, we don't only have to consider for corresponding to this state's phi plus or minus phi, but we also have to consider e to the ix times phi. So we could have an arbitrary phase like this. And okay, so that's what this definition takes care of.